a speed bump, you hit a speed bump, you hit a speed bump, you hit a speed bump. Such questions can be asked in JEE. Do you realize that over here in different directions, the refractive index, you're not a human, you're a donkey. Hello everyone, welcome to Catalysis by Vedantu. My name is Pahul and I am an alumnus of IIT Bombay. And today we are going to learn about a very interesting chapter. It's one of those very few chapters in chemistry that you can visualize. You can imagine things and understand them. And the best of all, it is important for your JEE examination and your NEET examination. Even though this chapter is not technically a part of the NCERT anymore, it is still asked in JEE Mains, JEE Advanced and NEET directly. Okay? So unless and until NTA doesn't say that this is not a part of our syllabus, we will definitely consider it to be a part of our syllabus. Fine. So my dear friends, thank you so much for joining in. Today we will study the solid state. And before we study the solid state, I have a question for you. What are solids? How do you define solids? If a layman were to come to you and ask, bro, can you please tell me what is solid? Then how would you answer? What are those certain properties that you would say in order to define what's a solid? Do one thing. Take out your notebook and pen. Get ready to take notes. Get ready to learn about the solid state in this awesome class. Let's get into it. What thoughts did you come up with? What are solids? You must be thinking, sir, whatever is not a liquid, whatever is not a gas, it's a solid. Okay. So let's try to understand that scientifically, but before I give you the scientific definition of solids, the scientific characteristics of solids, let me set some expectations first. Alrighty. In this class, we will learn about the very basics. You will understand on a better level what are the properties of solids. What are the different types of solids? They can be based on the bonding that exists in the solid. They can be based on the arrangement that exists of atoms or molecules that are inside the solid. Fine. Also, at the same time, we will solve a few interesting and important questions because your examinations will ask you questions, so you should know how to solve questions. Fine. And at the end of the day, I will give you some homework and assignments. Fun assignments, okay? Nothing boring. I'll give you some fun assignments. And in this class, we will definitely get to know each other better. If you're attending my classes for the very first time, welcome. And in this class, you'll know what my teaching style is and you'll get to know me better and I'll get to know you guys better. Fine. So now let's come to this question once again. What are solids? These points are important. They might seem obvious to you, but please make sure you take out your notebook and pen and write these down. In case the class feels fast, you can pause it anywhere and write it down properly. Fine. What are solids? See, solids have definite mass, volume, and shape. Take this pen for instance. I can't bend it. It'll break my hands before I can bend this. It has a very beautiful definite shape. It has absolute mass, right? Now the thing is that if we compare this to a liquid or say a gas, gases are easily compressible. You can compress the gas so much that it turns into a liquid, liquefied petroleum gas. Whenever your car tires are hotter, the gas inside, the air inside wants to burst out, expand. Yes. So comparing with gases and liquids, solids are definite in shape, mass and volume. Fine. Their intermolecular distances are short. Okay. Whatever constituents are there in the solids, they can be molecules, they can be atoms, they can be ions. Intermolecular is just a word that we are using over here. Interatomic distance, interionic distance. Everything is fine, okay? So the intermolecular distances are short, okay? Chote distance, sitting very close to each other. Intermolecular forces are strong. Why would two molecules or two atoms or two things want to exist close to each other? Only if the forces between them are strong. But over here, I will put a star mark. There is something more that I need to discuss about this particular point. How do we define strong? We'll think about it, okay? Now, fourth point is, their constituent particles, atoms, molecules or ions, have fixed positions and can only oscillate about their mean positions. Alright? To give you an example, think about a classroom where the class is going on. Every student is sitting in his or her own chair, right? है ना? Every student is sitting in their own chair and or bench or whatever in their fixed position. And they are not just running around, isn't it? Unless it's a physical education class. But the point is that when the class is going on, students are in fixed positions. All they can do is move around, raise their hand, ask a question, maybe chat with their neighbor, maybe pass some notes, whatever. But they're not moving out of their seat, right? So they have fixed positions, but they can oscillate about their mean positions. Fine. Something similar happens in solids as well. Solid molecules or atoms or ions or whatever are the constituents of a solid. If you heat them up, their oscillations will increase. For example, if you heat up a cooker or a pan in your kitchen, right? What happens is the molecules inside that solid are oscillating a lot. Does the pan turn into liquid? No. Okay? They are relatively incompressible and rigid, again compared to liquids and gases as we discussed in the first point. Now coming to the third point once again, intermolecular forces are strong. Think about water. At room temperature, water is a liquid, but when you cool it down below 0 degrees Celsius, it turns into ice solid. Now, what are the forces of attraction between two different water molecules? One water molecule is attracted to another water molecule with the help of hydrogen bonding. Yes. Now when I cool it down, it is still hydrogen bonding. You're not introducing a new, stronger force between two atoms of, two molecules of water, right? The molecules are still attracted by hydrogen bonding. How did hydrogen bonding become stronger at lower temperature? Do you realize the word strong that we're using over here is weird? Let me give you a scientific perspective to this. See, in chemistry, everything is relative. Everything is based on the conditions that you have around you. Stability, instability, strong, weak, acidic, basic, etc. All of this is relative. It depends on the conditions around you. There are certain things that are stable at higher temperatures, other things are stable at lower temperatures. I'll give you an analogy, very weird one, but it's interesting to think about it. You know apples? Not electronic apple, the fruit. Apples, they grow in relatively colder temperatures. Okay? In the hills, you will find lots of apple orchards. And wherever the temperature is colder, you will find better tasting apples over there. On the other hand, if I talk about mangoes, mangoes grow in relatively hotter climate. Okay? You will find mango cultivations where the climate is hotter, and hotter is the place, generally the mangoes are better over there. So mangoes are stable at higher temperatures, apples are stable at lower temperatures. Both of them are fruits. Point being that different things act differently at different temperatures. So over here what's happening in the case of water is, when you have water at room temperature, the energy of the molecules themselves is high enough so they can move around. Even though they are still connected by hydrogen bonding, they can move around fairly well because their own energy is high because of the higher temperature. Do you remember this statement from 11th class, states of matter? Temperature is essentially the amount of internal energy contained inside a system. If you don't remember, please revise states of matter from your 11th class. Okay? So, at low temperatures, sub-zero, below 0 degrees Celsius, the water molecules themselves don't have enough energy to move around. So, in that case, the hydrogen bonding takes over and keeps them in certain positions. Get the idea? Chalo, scientist's perspective always makes things a lot more fun than they actually appear. Now let's discuss what are the different types of solids. You can classify types of solids in two different ways. One is based on the arrangement of molecules, and the other is based on the type of bonds. Fine? Let's get into it and we'll understand it better. Based on the arrangement of molecules, there are two different types of arrangements over here. Again, take the word molecules with a pinch of salt, because in solids you can have arrangement of atoms, arrangement of ions, etc. Okay? So over here the constituent particles of the solid are arranged in a very beautiful, very orderly fashion, right? Hexagon, 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 hexagon. Looks nice. On the other hand, this arrangement is random, quite haphazard. Can you see? I am sure it reminds you of something. This classification is something that you've already studied in earlier classes when you were studying about the allotropes of carbon. This arrangement, well defined, will be called a crystalline arrangement. Yes. And the other one would be called amorphous. Got it? Crystalline arrangement, well defined, amorphous arrangement, sort of random. Both of them are solids, by the way. Okay? This is a random arrangement, but the atoms or the constituent particles are still close to each other. Okay? Random arrangement does not mean, okay, now it's a liquid. If the constituent particles are still close to each other, they can have a random arrangement and still be a solid. And the perfect example that you already know is diamond versus charcoal. Yes? Hira, koila. Coolio? Fine. So now let's discuss a few more properties based on crystalline versus amorphous nature of different solids. By the way, please make sure you are taking down notes. Notebook, pen, 2 different colors of pen, even better. Write things down. Okay? I don't want to handicap you by giving you my PDF, because I'll teach it in like 10 slides or something. You can write down the entire information of today's class in 2 slides. It'll be easier for you to revise from your own notes. You will remember things better when you open your notebook. You'll be like, now I know. Okay? You are the one who has to take the examination. Your efforts will make sure you succeed. My efforts will not ensure anything. Okay? My efforts might ensure my success, my views, my popularity, my salary, etc. Your success will be defined by your efforts. So please take notes. It'll be very beneficial to you later on, especially when you want to revise chapters. Okay? Chalo ji, this is a table that you might have seen in NCERT of solid state. I know I told you that solid state has been removed from the NCERT, but still older NCERT PDFs are available online for free. So you can also download them. Crystalline solids versus amorphous solids. Different properties are given. Let's study this table and understand it one by one. Shape. Crystalline solids will have definite characteristic geometrical shape. This is such a tongue twister. Okay, definite characteristic geometrical shape. For example, think of a diamond. It has a very nice shape, right? This looks more like an ice cream cone, but yeah, you get the idea. Very beautiful shape. If you break it into smaller diamonds, it will still have a very beautiful characteristic shape. Okay? It's because the atoms are well arranged. So no matter how you break it, it'll still give you that same beautiful geometric shape. On the other hand, amorphous is like, yeah, whatever. Irregular shape. Diamond versus coal. Always keep that image in your mind. Melting point. Since the shape is definite, throughout the entire solid you have the same type of arrangement. So the solid, when it melts, it'll melt at one sharp characteristic temperature. Okay? So imagine there is a solid which melts at, let's say, 650 degrees Celsius. Imagine. Crystalline solid. What will happen? 649 degrees Celsius, everything is solid. 651 degrees Celsius, everything is liquid. Because all the atoms are arranged in the same way. So all of them will follow the same type of physical nature. Okay? At the other end of the spectrum, you have amorphous solids gradually soften over a range of temperature. So what happens with amorphous solids is, let's say you have an amorphous solid. At 500 degrees Celsius, let's say it starts to melt. But at 500, only a certain part of that solid will melt. At 550, more solid will melt. At 600 now, more solid has melted. At let's say 610, the entire solid melts. Different parts of the same solid, amorphous solid, are arranged differently. So it will take different energies to melt these different parts, okay? So therefore, they don't suddenly melt at a specific characteristic temperature. It happens over a range, gradually soften over a range of temperature. All right. Cleavage property. Cleavage means to break something, to cut something into two. When you cut crystalline solids with a sharp-edged tool, they will split into two pieces. And the newly generated surfaces are plain and smooth, characteristic shape. Whereas on the other hand, like charcoal, if you cut it into two pieces, totally irregular. Diamond, charcoal. Always keep that example in your mind. Heat of fusion. What is fusion? Chemists just want to sound fancy. Okay? Fusion is nothing but melting. They have a definite and characteristic heat of fusion, again, because their structure is uniform. They will melt at a certain temperature. Okay? Same thing. Second point, this point, same. They don't have a definite heat of fusion because different segments of your amorphous solid will require different amounts of heat. Anisotropy, this is very important. Okay, this is very important. This is something new. These are anisotropic in nature and amorphous are isotropic in nature. Let's first understand what does anisotropic and isotropic mean. I will give you a beautiful real life visual while explaining anisotropy. So hear me out. First of all, let's write the definitions. It's important for you to write the definitions. Please write them. Pause the video anywhere you want. Anisotropic. Electrical and mechanical properties are different in different directions. Crystalline solids. Isotropic. Electrical and mechanical properties are same in different directions on an average. Let's try to understand this with a certain diagram. And after the diagram, I'll show you the real life example here in the class itself. So I'll draw a diagram over here. Please make sure you draw it in your notebooks as well. So let's try to make a hypothetical arrangement of crystalline solid. Atoms or constituents of a crystalline solid. Let's make a hypothetical picture, something like this. Fine. Can you see well-defined arrangement? Nice rows and columns. Okay. Now let's say I shine light onto this particular solid. Okay, I've zoomed into the solid. Now I can see the arrangement of the constituent particles of the solid. And now what I do is I try to shine light onto this solid. First, I will shine light in this particular direction. So what will happen? Now, remember refractive index. What's refractive index? When light goes from one medium to the other, it bends, right? It bends, right? Fine. Basically, the way it's interacting with the medium from one medium to the other, it's different. To think about the very, very basics of it, light is electromagnetic radiation, isn't it? It has electric field and magnetic field oscillating 90 degrees to each other. 11th class में कभी तो पढ़ा होगा आपने ये. Now, when this electric field and magnetic field comes close to the atoms of a medium, what do these atoms have? These atoms have electrons. So there's a certain interaction that might happen over there, yes? And depending on how dense or how rare is the medium, yeah, there will be more atoms or less atoms in a certain space, and therefore the interaction of the electromagnetic wave with the electrons of the material will be different. Just a very simplified explanation, okay? So what is going to happen over here if I shine light in this direction? Let's say it comes and interacts with this particle first. It bends a little, interacts with this particle, bends a little, interacts with this particle, bends a little, so on and so forth. Yeah, fine. You can imagine as if you are driving a car. Okay, you've turned into a tiny little microscopic particle with a microscopic car and you're driving in this direction, and then you hit a speed bump. Okay, speed breaker aaya, you cross the speed breaker, you travel for a little more time, another speed breaker, you travel for a little more time, another speed breaker, another speed breaker. Between each speed breaker, there's a certain amount of distance. Now, If I shine light in this direction, do you see the interaction will be slightly different? Light hits here, then it's here, it's here, it's here. Imagine the car versus speed breaker example again, okay? You are traveling here, you hit a speed bump, you hit a speed bump, you hit a speed bump, you hit a speed bump. More speed bumps over here compared to this direction. In the same amount of length. Getting the point? Over here your ride will be something like this. Over here your ride will be something like this. So in different directions, the physical property over here, refractive index, is different. And this, my dear friends, is what we call anisotropy. When the arrangement is specific in nature, in one direction you will have a certain type of arrangement, but in the other the arrangement is slightly different. Yeah, it's well ordered, it's well defined in three-dimensional space, but in different directions you will have different type of interaction. मान लो diagonally आया तो you will have a certain different type of interaction. Fine. Similarly, if you want to think about compressibility, you can compress this easier in this direction, but in this direction you won't be able to compress it. Yeah. Over here you have more spaces to compress. Over here you have less spaces. Anisotropy. Now let me give you a real life example. Have you heard about I'm sure you have. You've read about the defects of the eye. Myopia, hypermetropia, astigmatism, right? And what happens in astigmatism is the lens of your eye is supposed to be round, but it gets elongated. It turns into sort of an elliptical shape. Okay? Why does this happen? Because certain muscles of the eye become weaker, so it can't hold the lens in its proper round shape, so it becomes a little elliptical. Some muscles become weak, some become strong. So what happens is, since now the lens is misshapen, the entire world looks a little misshapen to the people who have astigmatism. I have the defect called astigmatism in my eye. Okay? Now for astigmatism you get cylindrical lenses. Okay? What that does is it refines the image only in a certain direction. Okay? Say your lens was supposed to be like this, now it's like this. So in this direction your lens will make the image better for your eye. Now in astigmatism you have multiple axes of lenses, okay, because different people will have different directions of astigmatism. For example, if in my eye it's like this, in someone else's eye it might be like this, it might be like this. Yeah, getting the point? The lens can get distorted in different axes. Even my two eyes, I have different axes. Okay, so now let me show you how the spectacles I'm wearing are anisotropic in nature. Let me show you. I'll come close to the camera. Can you notice this image? Okay, when I move around the glass, can you see how the image moves? Yeah. Do you realize that over here in different directions the refractive index is different? Yeah, समझ आ रही है? I'm changing the direction of the glass. The entire image that you see is changing. Anisotropy. Got the point? Some people might be saying, sir, but glass is amorphous solid. How can this be anisotropic? This is made with a special type of polymer. Okay? Which is not perfectly crystalline, by the way. It's almost crystalline. More about that later in the chapter of polymers, perhaps. Cool, so this is anisotropy. Let's come back. Electrical and mechanical properties are different in different directions. We've understood that. We've seen that properly now, and it happens in the case of crystalline solids. But why do we see isotropy in amorphous solids? You'll be like, sir, didn't you just tell us that amorphous solids are different everywhere? So aren't their properties supposed to be different everywhere? See, the thing is, look at this on an average. That'll clear away your doubt. What's happening in amorphous solids is that the arrangement is so random. Yeah, the arrangement is so random that no matter what direction you go in, you'll find the same amount of randomness. Okay, no matter whether you go in this direction or you go in this direction or in this direction, for every direction, overall, on an average, you will face the same amount of randomness. For example, if you are at a mela, you understand mela? A fair or a festival or whatever you want to call it. Okay? What do you call it? Carnival? I don't know. But anyway, if you're at a mela and if you want to go from this point of the mela to the other point in the mela, you will find a lot of traffic in the middle. Yeah, as in lots of people in the middle. Some places will be too crowded, some places will be less crowded. If you cross a stall, it will be very crowded. Other places might be empty. So from this point to that point, overall, you will face a certain type of arrangement. Equally likely, if you go in this direction, again, you will face some crowded spots, some empty spots. Overall, it will be same as this direction, same as this direction. If you zoom into a certain area, let's say, then you will find some order. Then you will find some pattern. For example, you come to a place in the mela where there is a very popular stall. So over there, people will be arranged, let's say, in a queue, waiting to get to the stall. Fine. So over there, you might find some arrangement. There might be a show going on at the other corner of the mela where people are sitting in properly arranged chairs. So there you will find some order. But overall, the amount of randomness in every direction is going to be the same. And that is why we say that amorphous solids are isotropic. Isotropy bole to same. Iso means same. Same in either direction. And iso means different in either direction. Okay. Coolio. This is done. Fine. And isotropy explained. And with this, the last 2 points of our table become very, very simple. Let's come to the last point first. Order in arrangement of constituent particles, long range order. Through the long range, the ordering of your atoms is same. Short range order, as I gave you the example of the mela. Only in short spaces, you will find some order, but overall there is a lot of disorder. Got it? And then when we say nature, this is a figure of speech. Okay? For example, when you meet a person, you'll be like, this is a genuine person, this is a true person. Very nice. Similarly, when you meet a crystalline solid, you'll be like, wow, definite shape, definite melting point, nice. Sophisticated, plain surface, smooth, definite, everything nice. Yeah, you are true solid. But on the other hand, if you meet an amorphous solid, you'll be like, bro, what the hell? You have very irregular shape. You don't even have a proper melting point. You melt over a range of temperatures. When I cut you with a tool, you're irregular. There's nothing definite about the amorphous solid. So then you're like, you're not true solid, man. You're fake solid. So it's just a figure of speech, pseudo solid. Pseudo is just a fancy word for fake. I'm sure you've studied that word, pseudopodia, fake feet somewhere. So pseudo means fake, okay? Pseudo solids or supercooled liquids. Now this part is a big misconception that people have. Supercooled liquids are actually solids. Okay, there are some liquids that are very viscous. Sometimes those viscous liquids are called supercooled liquids, but that's not where this term is used. Supercooled liquids is used for solids that are not true solids. Figure of speech. For example, you might meet a person and you'll be like, you're not a human, you're a donkey. Does that make that person a donkey? No. Is that a donkey who is very much like a human? No. That's a human being who you think is a donkey because of whatever. Yeah. So over here the same thing is happening. You meet the amorphous solid, you're like, you're a fake solid. You're not even a solid, you're a liquid, man. Does that turn that solid into a liquid? No. It's just something that you're calling that solid to make it feel bad. Get the idea? So supercooled liquids are essentially solids, and one very Interesting example over here, a big misconception that people have is about glass. Yeah, people say that glass is a super cool liquid. Over the years, when you look at window panes, the bottom part of the window panes is thicker because the liquid has flown towards the bottom. That, my dear friends, is a misconception. Glass is a solid. It is a proper amorphous solid. In ancient days, what used to happen is that their glass making techniques were not mechanized by machines, for the lack of better words, done only by human hand. Okay? I'm sure you've seen how they make glass. They put it in a furnace, they melt it, looks very beautiful. Yeah. What happens there is, in ancient times, when they used to make glass, to make sheets of glass, they would spread it on a table. The table would never be perfectly level. Yeah. There's nothing perfectly level in this entire world. Something or the other is always askew. And in old days, they didn't have lots of tools either to worry about that stuff. Yeah. So naturally, while the glass was liquid and it was solidifying, glass is very hot when it comes out of the furnace. So it's a liquid at that point of time. So at that point of time, because of the not so level surface, it would become a little thicker on one end, and on the other end it will be slightly thinner. Now when the carpenters or masons or whatever would put it into glass panes, obviously they would keep the thicker end at the bottom to make it more stable. Yeah, this is more stable, right, compared to this. This is more prone to bouncing around and falling. So that is why in those buildings people have found the bottom ends to be thicker. This is the actual reason. So glass being a super cool liquid and it flowing through the years is a big myth. Keep it in your mind. Chalo ji. Question. Classify the following as amorphous or crystalline solids. Polyurethane, naphthalene, so on and so forth. I'll solve the first 4 for you. The rest are your homework. I'll tell you how to do the homework later. But first of all, polyurethane. What is polyurethane? Foam. Foams inside the mattresses. I have this thing over here. This is a taken out of a sofa or something. It was lying in the studio for some reason. So yeah, what's inside it? It's foam, right? I can't open it because I'll have to tear it apart. But there's foam inside it, okay? So foam is made out of a polymer called polyurethane, okay? And the easiest way to imagine whether something is amorphous or crystalline is amorphous solids tend to be a little softer. They break easily, and you break them, they have very irregular shape. Polyurethane is amorphous in nature. I have some images of it over here as well. ठीक है? Soft है. So crystalline solids would tend to be hard, isn't it? Then comes naphthalene. Everyone has seen naphthalene. Naphthalene balls. In Hindi we call it phenyl ki goliyan. Right? So naphthalene crystals, very beautiful crystals. When you break it, you can see those crystalline surfaces. They reflect the light very nicely. Yeah? Definite. Crystalline. Okay? Harder. Crystalline. Benzoic acid. A lot of you must be wondering, sir, shouldn't this be a liquid? Acid सोच के ऐसा ही लगता ना कि कुछ तो liquid सा होगा. But benzoic acid, when it is not dissolved in water, when it is anhydrous, this is how it exists. Tiny, tiny shards of glass kind of thing, okay? And these shards of crystal are crystalline, okay? Teflon. I'm sure you're wondering, sir, but how would we know? I'll tell you, don't worry. Teflon. What is Teflon? Tetrafluoroethylene, a polymer that is used in non-stick cookware. But then you're like, sir, but it is stuck to the cookware, so we don't know whether it is soft or hard or what. Have you seen these tapes? If a plumber has come to your house to repair your taps or something, they carry these tapes generally. These are Teflon tapes. These are used as sealants. These are very flexible, by the way. Very soft, very flexible tapes. You keep stretching them, they'll keep stretching till eternity. Okay? So whenever the tap has to be screwed in, to make that joint waterproof, they put Teflon tape over there. Okay? So Teflon, very soft, very stretchable. Obviously, it's got to be amorphous, right? Crystalline won't be soft and stretchable. So my dear friends, over here you notice that polyurethane, Teflon, both are polymers. In the creation of polymers, what happens is something called cross-linking can happen. Okay, it happens in most of the cases of polymers. Okay, some are more cross-linked, some are less cross-linked. So what happens is this weird thing happens. Can you see how chains of carbon, the basic structure is chains of carbon in polymers. You'll learn more about it in the chapter of polymers. But right now, just for your visualization, okay? Can you see how random this structure is? No matter how specifically you do polymer generation, they can be made crystalline only to a certain extent. Overall, they're always amorphous. For example, this glass. This is crystalline to a good extent, but overall it is still amorphous. Okay, there'll be lots of order inside this, but there'll still be places of disorder, because humans are not perfect. That's the best explanation that I can give you. Polymer generation process is not perfect. It does not generate perfect crystals as such. Okay, very sophisticated processes have to be done to make crystalline polymers, and those are difficult. They have to be done in the laboratory, and only small fragments of crystalline polymers can be created. Over a long range, they are always going to be amorphous. You can read more about it on the web, and you can find some research papers on it as well. ठीक है जी, चलो. So the first 4 I have done for you. The rest you have to do on your own. How? I will tell you later, but please make sure you take a screenshot, note it down, whatever you want to do. Now, let's classify based on the types of bonds. What are bonds? पहले तो ये बताओ, what are bonds? James Bond. So when it comes to bonds, let me take you back to the chapter of chemical bonding. Now you must be saying, sir, oh, ionic bonding, covalent bonding, metallic bonding. But what is a bond essentially? Bond is a name given to an attractive force that keeps atoms together. Yeah? Basically, it's an attractive force, right? Which is keeping 2 or more atoms together. So, you could have different types of bonds. You could have covalent bonding. Yeah. You could have metallic bonding. Whatever, ionic bonding. Why am I writing it? Covalent bonding, everyone knows there is sharing of electrons. Let's take the example of H2 gas. Sharing of electrons between 2 hydrogens. So this sharing of electrons is what keeps them together. That's why they're attracted to each other, because they're sharing their electrons with each other. If I talk about an ionic bond, Na positive, Cl negative, they are keeping each other together because of the positive and the negative charge, right? When we talk about metallic bonds, let's say you have sodium, 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 Batman. Okay. Any one of you got the reference? Na 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 Batman. Okay, maybe too old for that reference. Maybe I am too old. But anyway, coming back to metallic bond. So metallic bond is a little more complicated. I am sure you remember valence bond theory and molecular orbital theory from chemical bonding. What happens in molecular orbital theory? Atoms come together, their individual atomic orbitals combine to create molecular orbitals. The arrangement of electrons in those molecular orbitals is more stable, and that's why they form molecular orbitals. So, something very similar happens in metals, wherein multiple atoms of metals come together. Multiple atoms combine their multiple atomic orbitals together to create multiple molecular orbitals, and in those molecular orbitals, electrons exist very nicely and freely. Overall, if you want me to make a better explanation of metallic bonds, I can create a separate video on that. Metallic bonds, technically the details of them are not in your syllabus, so that's why I'm not going too deep into them. But if you want me to create a video on them, I'll make like a 5-10 minute video explaining metallic bonds to you in a better way. So if you want that, please leave a comment down below. So now there's another category of forces that we might have forgotten. Do you remember hydrogen bond? Yeah, we just saw that a little while ago in the case of water. Hydrogen bond. Yeah. What's going on over here? Basically, you have a dipole which is attracting another dipole, isn't it? Partially positive character on hydrogen, partially negative on oxygen, partially negative, partially positive attractive force. This attractive force is because of positive character of hydrogen attracting positive character of, negative character of oxygen. Why do we have this positive and negative character? Because of the electronegativity of oxygen. Both the electrons in this bond are more towards oxygen, therefore it has a negative character on it, and so on and so forth. Yeah. So when hydrogens are involved in dipole-dipole interactions, these are known as hydrogen bonds. You could have other interactions as well, by the way. You could have van der Waals forces. You could have induced dipole to induced dipole interactions. You could have London dispersion forces. Yeah, all of these are very similar to each other. If you don't remember them, please go back and revise chemical bonding. Preferably read the first 5 to 10 pages of it from the NCERT. A lot of detail about all of these forces is given very beautifully in NCERT. Fine. So please revise chemical bonding once. Okay. So you have hydrogen bond or van der Waals forces or London dispersion forces or dipole-dipole interactions, etc., etc. So we've basically come up with 4 different types of bonds or attractive interactions: covalent, ionic, metallic, and others. Okay. So with these 4 different type of interactions, we can make 4 different types of solids. First one we can say would be covalent solids. Best example is diamond. Yeah, because carbon, 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 carbon all attached to each other with covalent bonds. One carbon is attached to 4 more carbons. Everyone knows the structure of diamond, right? So covalent solid, best example is diamond. Then if I come to ionic solids, the best example would be NaCl. Na positive, Cl negative. If I come to metallic solids, everyone knows almost all solids are, almost all metals are solid in nature, right? Sodium metal, a little soft but solid. This is a metal, iron, aluminium, etc., etc. So everyone knows. Whatever. Mercury is a liquid, gallium melts easily, whatever. Metallic solids, everyone knows. Then the last category, the others category, these are called molecular solids. So most of the things that exist as liquids or gases at room temperature, when you cool them down, they turn into solids, and those solids, more often than not, are molecular solids. For example, if you take argon gas out of the atmosphere and cool it down so much that it turns into solid argon, that will be a molecular solid. Dry ice, everyone knows about dry ice, right? Solidified carbon dioxide. When you bring the molecules of carbon dioxide together by cooling it down, molecular solid. Let's explain this better with an example. My dear friends, if I talk about water, H2O, what kind of a solid is it? Is it covalent? Is it ionic, metallic? Obviously, water is not ionic, water is not metallic. So is it covalent or is it molecular? Most of you would have the correct idea, I'm sure, but some of you might not have the correct idea. Some of you might be thinking, sir, in water, oxygen is bonded to hydrogen with covalent bonds, therefore it is a covalent solid. That's not the correct explanation. Don't worry if you got it wrong, I'll correct you. And if you got it right in the first go, brilliant, no problem. See, this is just one molecule of water, right? The atoms of this molecule are held together with covalent bonds. That's fine. But when you talk about one molecule sitting close to another molecule when the temperature is cold, then my dear friends, the interactions between two molecules is hydrogen bonding. So when individual molecules are coming closer to each other and sitting together with the help of van der Waals forces or hydrogen bonding or dipole-dipole interactions or whatever, then my dear friends, we call them molecular solids. Fine. Now let's see a nice table, different types of solids, what are their constituent particles, what are the attractive forces, examples, physical properties, etc., etc. NCERT table, You can write it down with me while I explain it. You can pause the video anywhere. Let's zoom it in a little. First type of solid that we'll talk about is molecular solid. What are the constituent particles? Molecules. What are the type of attractive forces? All of these weak attractive forces. Fine. According to these weak attractive forces, you can have different types of examples. Dispersion forces or induced dipole forces, argon, carbon tetrachloride, hydrogen, iodine, CO2, all of these, if you cool them down and solidify them, they will turn into solids. Dipole-dipole interactions, molecules other than water, for example, HCl, dry HCl, dry SO2, sulfur dioxide. These are polar molecules, dipole moment, chemical bonding. Please revise. Hydrogen bonding, H2O, ice is an example. Solidified ammonia would also be another example, right? Cool. So, physical nature of these, from the very weak forces, you'll get softer solids. From slightly stronger hydrogen bonding, you'll get a harder solid. They won't be as hard as diamond, of course, but harder. Fine. Electrical conductivity. Insulators, they do not conduct electricity. Remember, water does not conduct electricity. When you dissolve salts into water, those ions move around to conduct electricity. Water on its own, be it liquid or be it solid, they don't conduct electricity. Fine. Melting points are low, obviously, because the attractive forces are not that strong. So you provide them a little bit of heat, room temperature, they turn into liquids or gases. Ionic solids, people. Obviously, the constituents are ions attracted by electrostatic forces. We can also call them Coulombic forces. All these salts, NaCl, MgO, ZnF, CF2, all salts, ionic solids. They are hard, but they are brittle. Hard, but they can be broken very easily. Okay, hard and soft, you understand the difference. Soft is spongy, squishy, hard is hard. Okay, so these are hard, but they are brittle. They can be broken very easily. So if you take rock salt, you throw it on the floor, it will just scatter into pieces. You can buy crystal salt from the market. It's not very expensive. And if you take that crystal salt in a mortar and pestle and you grind it, is not the correct word, but yeah, you understand, right? So if you do that, if you pulverize it, then it will turn into smaller crystals of salt, right? They are insulators in solid state, but conductors when you melt them or in aqueous solutions. Solid state mein, as we studied earlier, constituent particles are in fixed positions. They can't move around. They will move around only when you melt them or dissolve them in aqueous solutions. Fine. Melting points are high because ionic bonds are strong. So to take these constituent particles away from each other, to melt them, it's a little difficult. Chalo ji, aage badhenge. Metallic solids, positive ions in a sea of delocalized electrons. That is why I said I'll make a separate video on metallic bonds. No one's gonna ask you too much about metallic bonds in your syllabus. Different metals are given as examples, obviously. They are hard but malleable and ductile. Yeah. They are hard overall, generally. Sodium is softer. Yeah. Gallium, mercury, they can melt very easily. But they are malleable and ductile. You can bend them into wires. You can flatten them into sheets. Malleability and ductility. Right? Conductors in solid state as well as in molten state. Because of these free electrons, delocalized electrons, melting points are high. Most of them, melting points are high. Some exceptions obviously exist like mercury, gallium. Chalo. And then covalent or network solids. They are also called network solids. Why? We'll see an image in a couple of slides. You'll know why. So atoms are the constituents. They are connected to each other with covalent bonding. Some notable examples, of course, are diamond, SiO2, silica, SiC, carborundum kaha jata hai isko, we call it carborundum. I'll show you the name later. Aluminium with nitrogen, nitride. Graphite is an example. And my dear friends, they are hard, they are insulators, their melting points are very high. Only exception over here being graphite, because graphite is a little soft. Yeah, that's why you can write onto your notebooks with graphite. Yeah. It's a conductor, exception because there are lots of delocalized electrons. Imagine graphite as lots of benzene rings joined to each other. So there are lots of delocalized resonating electrons that can flow around. More about those details in organic chemistry, by the way. Okay? Even graphite melts at a high melting point. Okay? So exception only in the case of being soft and being an electrical conductor. Coolio, this is done. A few zoomed in pictures for you of the arrangement of constituent particles. This is an example of NaCl, ionic solid. Small ones are sodium, bigger ones are chlorine. This is how they are arranged in space. When you zoom into NaCl crystals, this is what you will see. If you can make a powerful enough microscope to see, but you get the idea. Same type of atoms. Copper can be arranged this way. Metallic bonds will basically look like this. Their arrangements might be slightly different. We'll learn more about these arrangements later. But metallic bonds, okay? Same type of atom repeated again and again. Covalent solids, network solids, okay? Diamond, everyone knows about diamond. Silicon dioxide or silica. Silica exists in lots of different structures in nature. You find it in quartz. You find it in silica gel that you get in, those tiny pouches that prevent moisture from getting into your bottle or a new box of medicines, etc. Yeah. So silica gel. You have different forms of silica. Yeah, it's present in sand, etc., etc. Silicon carbide, this is known as carborundum, as I told you. Okay, let me write the spelling for you so that you're not confused. They can exist in different arrangements in nature. Fine. Silicon carbide. Graphite, obviously everyone knows about graphite. Yeah. So this is why they are called networked solids. Can you see the network of atoms in each of these cases? There's a very beautiful, intricate network that's getting formed. That's why we call them networked solids. Okay, these are like their individual building blocks, so to speak. So I have a certain web page that I want to show you. Yeah, this is a Wikipedia article. Sorry for the sudden change in the color of the slide. Yeah, suddenly white might look very bright to the eye, but you don't have to remember any of these. Okay, this is a Wikipedia article for silica. Silica can exist as alpha quartz, beta quartz, tridymite, so on and so forth. Okay, and in all of them, they are arranged differently. SiO2 is arranged very differently in all of these cases. Crystalline. Very interesting. Okay, so you can read the Wikipedia article if you want. Okay, black ones are carbon, red ones are oxygen, lots of CO2s together. This is the example of a molecular solid, dry ice. Nice. This is also done. Now people, let's do a question. Solid A is a very hard electrical insulator in solid as well as in molten state and melts at extremely high temperatures. What type of solid is it? देखो जी, बहुत simple सा question है, very simple question. Solid A is a very hard electrical insulator. So it's an insulator, can't be ionic. It's an insulator in solid and molten state. Can't be ionic, can't be metallic. Metals are conductors everywhere. Ionic bonds are, ionic solids are conducting when they're molten. Also, this melts at extremely high temperature. So it can't be your molecular solid. Molecular solids are liquids and gases at room temperature. So what are you left with? This is basically your covalent or networked solid. An example obviously over here could be diamond. Fine? Good enough? Simple question. Just revising whatever we've studied a couple of slides back. Another question for you. Classify the following solids in different categories based on the nature of intermolecular forces operating in them. Yeah, you have to basically tell ionic solid, covalent solid, etc. How many of these are covalent solids? Such questions can be asked in JEE. Sometimes even in JEE Advanced with more complicated examples. How can you ask these questions in JEE? As integer type. How many are covalent solids? That's a very beautiful integer type question. Can be asked as, match the column as well. You have left side as covalent, metallic, ionic, this and that. On the right hand side, you have different examples. Okay. Such questions can be asked in regular ABCD type of questions as well. How many covalent solids are there? 3, 4, 5, 6, whatever. Okay. So this is an important question for you to solve, and make sure you solve it on your own. This is your homework. And at the same time, this is your homework, by the way. How many of these are covalent solids? Answer this in the comment section, please. Leave a comment telling me the answer of this particular question. Fine. Badhiya hai. You can pause the video here, take a screenshot, write it down. Let's move forward. Now we have some tasks for you. Alright. First task is read the NCERT first 10 pages. I know it's removed from the NCERT, but older versions of the NCERT have this chapter beautifully written in them. You can find it online on google.com for free. NCERT's website has it for free. So all you need to do is go to google.com, search for solid state NCERT PDF. You'll get it. Okay? So read the first 10 pages from there. Solve the given questions via a web search. What do I mean by that? For example, this question. There are so many different substances that are given to you. Do a Google search for all of these substances. Search for potassium sulfate. See what it looks like. Read about it. Understand it. Not much. Don't do PhD on each of these elements. But at least look at them. Read the first few lines of the Wikipedia articles. Look at what their images are. What do they look like? What are the different forms in which they can be present in nature? Yeah. So for all of these, search for ammonia. Search for water if you want to. Rubidium, argon, silicon carbide, etc., etc. Similarly, for this particular question, you have to search for all of them. Otherwise, how will you know what do they look like? Where are they used? Why are they used for whatever they used for? And you might be wondering, sir, how is that important for us? You live in this world, right? These things exist in this world. It's important for your brain to feel curious about things. Otherwise, everything in this entire planet or in this entire universe is useless, right? So for the sake of your curiosity, for the sake of scientific thought process, for the sake of growing your own mind, search for these online, read about them, have some fun while learning chemistry. ठीक है जी? तो do the questions via a web search. Revise your notes before the next class. When will the next class be? A day after this class at the same time on the same channel. Fine? And please subscribe to the channel. You'll get the notifications automatically if you click on the bell icon. Comment what's your current favorite song. Just for fun, okay? I just want to get new songs to listen to. So yeah, just comment your current favorite song. And what's going to happen in the next class? People, in the next class, we are going to go further in this chapter and understand what is a unit cell. Very important. This forms the basis of most of the questions of solid state. What's a unit cell? When we arrange unit cells together, we get something called the lattice. What is a lattice? How do you define a lattice? What is meant by lattice? We'll understand the meaning behind these images. Why do we have to study them? Tetragonal, orthorhombic, what's going on? We'll learn about all of this and much more in the next class. So people, I hope you enjoyed today's session. It would definitely be different from other chemistry classes that you've attended from other teachers, because the way we think is like scientists would think. So people, if you enjoyed it, make sure you hit the thumbs up button, say subscribe to the channel and leave a comment. You know exactly what to do, right? So I'm going to see you in the next one. Until then, peace out.